Hey guys, it's just a quick video going over the changes I made to the notebook as well as all the processes I did, and basically just keeping you guys caught up on everything that's happened over the weekend. So to start things off, Kevin put together the combined flight data spreadsheet based on the government websites. I forget, I'm blanking on the name. But basically, it contains all of the flight data for 2024 and a ton of extra features and columns that we can look at. And in case you're not aware, if you're curious about what any of those fields mean, you can look at this spreadsheet that Kevin posted that basically goes over what each field means, so that we know, what is that information, because some of them are kind of confusing. They don't really make sense just to read it, so that's always useful if you're ever confused. So anyway, of course, up top, we're loading in that new data set. Now, here's the deal. I didn't want to remove the code related to the old data set, the Kaggle data set. So all of that stuff is still here. I think ideally we can port a lot of it over to use the new data set, but given that the field names, they don't match up. They have totally different columns, so we need to basically port that over. It shouldn't be too difficult. I just haven't been able to do it yet. But anyway, if you scroll about halfway through, right after this red and blue plot, you can see that from this point on, we're using the new data. So everything past this point has to do with the new data. Everything above this is the old data. So you don't need to worry about any of this as far as like the next presentation is concerned. Don't pay attention to anything above this point. So just to get started, we can see the basic information about the data set. We can see all of the columns as well as the data types that they're in, as well as just a quick snapshot of what the data looks like. And then the first thing I wanted to do is define our goal, because we want to create a model that can ideally be pretty versatile. Maybe it can predict different types of delays, different types or conditions for cancellations and stuff like that, because that data is captured in our data set. Like you can see, we have, obviously in this cases there wasn't a delay, that's why it says not a number. But if there was a delay, I think carriers, that's like the airline, a weather delay, or any other type of delay, we would have that information. But that's pretty complex, and we would basically need a separate model for all of them. And I just wanted to have, for this week 2 presentation, a single unified model that basically is just predicting, was a flight canceled or delayed? So I engineered this new column called is impacted, and this is our target variable. So if the flight was canceled, or if it wasn't canceled but it had some sort of delay, it doesn't matter what kind, that was 15 minutes or more than 15 minutes, we consider the flight impacted. And by the way, this definition, the 15-minute delay, counting as a delayed flight, that is from the bts.gov website. So they consider if a flight has a 15-minute delay or more, then it counts as a delayed flight. So yeah, obviously sometimes you're going to have a flight that's like 1 or 2 minutes late, so we're not counting those, obviously. And you can see roughly, I want to say it's like 20% or something of the flights have some type of delay or cancellation. And you can see in some cases we have flights with negative delays. That basically just means that they're ahead of schedule. So like if the flight was at 5 p.m. but it took off at 4:58, then that would be a -2 delay, which, that makes sense. So then I wanted to identify the features which we want to use to train our model. Now, what we needed to do was identify which columns have anything, like have information that we would know about the flight before the day of. So like obviously we can't train it on the weather delay, because if we knew the weather delay going in, then obviously we know if it's going to be canceled or delayed or not, because we know what that information is. So we can only consider columns that is like information related to whether the flight, like the information about the flight, like when you book it. So we have time information like the year, the month, day of week, date, etc. We have the carrier, that is the airline, so like United, Southwest, or American. The origin information, so that's the airport and the state, destination, same thing. And then we have a couple of different time estimates. So this is the planned departure time, so like say 4:30 p.m. This is the departure time block. This is aligning it into an hour. So basically 4:30 and 4:45 both count as 4 p.m. for the departure time block. Same thing for the arrival time. The elapsed time, that's the estimate for how long the flight will be. Distance and distance group, same idea, the total estimated distance, and then the grouping into basically a bin of nearby groups, or of nearby distances. Is impacted, that's the feature we engineered earlier. Then we do our null data check. So we only need to check for nulls in the fields that we are using to predict is impacted. So we check all of the planned features, that's these, the flight information. We check for nulls. There was only one null value in the whole thing, the CRS elapsed time. There was a single flight that didn't have that. Honestly, I probably could have tried to fill it in, but I figured, well, we have 7 million flights, so I don't know, we could just clean it out. So I drop it out, and then you could see I verified that we didn't accidentally drop any extra anything. Everything worked as expected. All right, so on to feature cleaning and transformation. So the first issue I had, I didn't do this quite so much at the start, was that we have limited RAM, and this spreadsheet, not this spreadsheet, the spreadsheet that Kevin gave us, it is huge. There's 7 million entries over tons of columns. The data types in each column are quite heavy and expensive. And it doesn't load in Excel, it crashes Excel, right? That's how big it is. And we can load that full data set in its raw form into the notebook session, right? But we do have limited RAM and disk resources, and if you exceed that threshold, it'll just close your session and throw out all of your data. So I trained it a couple of times, and then things would just end up crashing, and I had issues. So basically what we need to do is we need to reduce the memory footprint of each column if possible. So the first way we're going to do that is by quantizing. So we have a lot of int64 and float64s. Those could be cast down to int and float32. There may be some quantization loss, but I kind of was thinking about it. It's probably pretty minimal, because we're not we're not doing anything that's like that precise. And I think overall it's more about minutes and hours, not about seconds, milliseconds, etc. So I think we'll be okay. I don't think we'll see tremendous loss. Technically, we could probably, well, I don't know. Maybe we could upgrade to like Google Pro or whatever. But realistically, like this isn't gonna be making or breaking our results. So this is just gonna be more efficient, and I think that this is fine. But then the second way we're gonna do this is label encoding. So label encoding, we have a lot of categorical columns. So things like, what is the airline? What is the origin airport, destination airport? All of these things. And it makes it quite heavy, both in terms of memory and in terms of the model itself. It's less efficient. And so what this basically is we take each I think they're strings in a lot of cases, and we cast them into a numerical value. but it actually works out okay. It doesn't, as far as I'm aware, it doesn't have any like major impact on the model itself because it can handle it basically. I'm not explaining that super well, but it improved our results and also it let us run it, so all good. So you can see, I think to start with, before we did any feature quantization or optimizations, we had 3 gigabytes of memory for our data set, and we got it down to 972 megabytes, which is a significant reduction, and it basically, yeah, it was pretty huge, and we didn't really lose anything by making that optimization, so all upside. I also did some basic feature engineering. The idea is that we want to convert the data format from these columns into something that's better processed by the machine learning model. So it's not like I'm creating brand new features by combining them. I strictly wanted to just basically make it so that these features were friendly to XGBoost. So it's basically, just changing around the data types, changing the way that it looks into a way that's better for the model. And speaking of the model, we're finally at that step. We are now training the XGBoost model, and we're trying to estimate that is impacted target variable I mentioned earlier. We have X as the list of features that we're using to predict, so that's that flight data, like the date, the time, airport, etc. And then Y is, of course, that target variable. Is the flight impacted or not? Next, we do what's called data stratification. So we need to split our data into test and training data. And it's a little bit more complicated than you'd think. In a lot of cases, like you could kind of like randomly split data, or say the first half of entries chronologically are training and the other half are testing. But keep in mind, we want to be able to use our model for any time of year. So if we trained on, say, the first 9 months and then tested on the last 3 months, like that's not going to work. If we train over the winter and then try to test in the summer, like that's not going to work. It's going to miss out on a lot of the nuances that come with the seasons. So the way I handled this is I made sure that we have a 70-30 split between training and testing, and the samples are picked evenly throughout the year, so there's an equal-ish amounts of samples from each time of year, and the ratio of impacted to non-impacted is preserved. So you can see the training, testing, and the training and the testing data, they each have the same proportion of is impacted to not impacted. So they have 78% not impacted and 21% impacted. So we finally get to the step where we're actually implementing and training the classifier. Not a lot to say here. I use the default hyperparameters just because I didn't really know what would be good yet, and I just wanted some preliminary results. So we get to the testing step, and here are our results. We have an 80% accuracy, which seems pretty good at first glance, at least for a first shot, but you have to remember, we have a 80-20-ish, I think it was 79-21% split of impacted to non-impacted, or sorry, impacted to non-impacted. And so this is actually not that much better than just guessing not impacted every single time. And you can see our recall is really bad. And basically what that means is that, yeah, we're overwhelmingly just guessing not impacted and getting a really good accuracy, but you can see your precision recall not so good. And so that's a problem that I want to solve. And so I went ahead and I did a little bit of analysis. I wanted to see what features had the biggest impact on our results. And something that was interesting is that the greatest proportion of impact is related to that departure time. So these are both related to departure time. That's in total 74% of the weight is in departure time. And then the next one is arrival time, which if you think about it is kind of related to the departure time in the sense that generally the arrival time is just going to be like a time shifted departure time. So the arrival time is like the departure time plus whatever the average flight duration is in the United States, if that makes sense. So overwhelmingly, we're capturing the time of day. And so, yeah, the time of day has a huge impact. And we saw that, by the way, in the week 1 data. We saw that as the day progresses, we get more and more delays because of that cascade effect. And I thought what was interesting is the month and the day of the year did not have a tremendous impact, which you would think like would have the, maybe not the most, but a significant impact, right? If it's the middle of winter, you're way more likely to have a big snowstorm that cancels all the flights or whatever, but it seems like our model either isn't capturing that information or that assumption is like somewhat faulty, so we'll have to, keep an eye on that because it seems like it wasn't picked up. Here's a visualization. I probably should have been showing this the whole time, but yeah, you can see departure time have the biggest share, arrival time, which is, yeah, anyway. I had Gemini produce like a little data analysis because I was like kind of having trouble interpreting what was going on, and it suggested some things we could do to improve, and so the first thing that I did for an improvement was addressing the class imbalance. Basically, there is, class imbalance. It's way more likely that you're going to be not impacted than impacted. And so we need to normalize according to that in order to boost our recall. So we calculate the ratio of negative to positive, and we use that to build a second model, except this time we're using that weight, that scaling, in order to get better results, at least better recall. So when we test, our accuracy went down, which is annoying to say the least, but our recall went up drastically. So now that we've adjusted for this, our overall accuracy may be lower, but when it is a impacted flight, we're much, much better at predicting it. And if you think about it, I think that this is preferable. I would way rather have a model that will sometimes tell me, hey, your flight might be delayed, and then it's not, than the opposite. It's kind of similar to when we discussed in class with like cancer validation. You would way rather have a false positive than a missed negative, or I might have that backwards. You know what I mean? It's way better that we catch cases where impact will occur than falsely guess that it will occur and then it doesn't. Once again, I asked Gemini to just put together a quick analysis to see if there's anything useful. I then went on to do cyclical feature engineering. So this was an idea that I thought was pretty interesting because I wanted to look again, I was talking earlier, I felt like we were missing out on those time-based phenomena. Like if it's the winter months, well, we probably should expect to have a greater proportion of canceled or delayed flights. We should see more impacts, right? And so this technique is to basically take our time-based features, so that's month, day, year, week, and turn them into sine and cosine wave components. So basically we end up scaling them into these into these sinusoids, and the idea is that it gives you, at least in theory, a better sense of cyclical time-based features. And so you can see I did it for month, day, year, day, week, blah, blah, blah. So I redefined the x and y vectors with the new cyclical features. I split the data again. And then I did hyperparameter tuning. So we, I've talked about this a lot in class, I think during the lecture portion, but basically I just wanted to see, can we get better results from hyperparameters that are like more optimal? So it takes a long time to run. I ran it last night. It took like an hour, maybe an hour and a half or something. So don't run this unless you're willing to sit through it. I accidentally ran it earlier. I actually clicked on it and there was like, oh crap, and I canceled it. So that's why this doesn't look right. I'll probably run this again tonight once we're done working on everything, just so that it's, we have it in the notebook, but it's not really that important. I have the results from that hyperparameter optimization here. These are the parameters it came up with. I don't really know if there's any significance to those, but basically I just wanted to take those and put them into a model and see if it improved our results. And the answer is, well, yes, but not as great as I was hoping. So this is our optimized classifier. This is the initial one. So yeah, let's start here. The initial one. This was that first one. We hadn't done any scaling or tuning. Everything was just basically as raw as it gets. This was after we scaled our target variable, after we normalized. And so that was when we got that recall boost. So really we're interested in comparing this one to this one. And unfortunately, I mean, it's better, don't get me wrong. We're getting 0.003 better recall. We're getting 0.004 better accuracy. So it's better. But honestly, we didn't get a lot of performance. And it's kind of not worth our time. I mean, we ran it. It took like, an hour or whatever. And we got basically, a fraction of a percent of performance gain. So, well, it was worth a shot. I then did a brief visualization of this to see if I could notice anything interesting. So you'll recall that the initial model technically had higher accuracy because it was pretty close to just guessing not canceled every time. But the new models are better at recall, which in my opinion is more important. So you can see we gave up accuracy and precision, but we gained a ton in recall and in F1. So it's a trade-off. I think it's progress, but honestly, I mean, what was our recall? It was 0.664. That's not great. I definitely think we could do better. I have some ideas on ways that we can improve our score. But those are going to take time, and that's stuff we could work on for week 3. Let's see here. What is this? Feature importance for the optimized model. So I wanted to see if our changes had increased the importance of the time-based phenomena. So if you recall, before we did the cosine and sine normalization, or sorry, not normalization, but you know what I mean. We turned the time-based stuff into sinusoids. We saw that the time-based features were way more important than the date-based features, and we still see that, obviously, but it is slightly improved. We're seeing that the time is less important as it was before, and that all of the other features have gone up in importance. So that's kind of cool. I'm sorry. I didn't expect this to go on for 25 minutes, but I felt it was important to keep you guys up to date because I feel like I kind of did most of the stuff for the week 2, and I'm nervous that if we go ahead into the PowerPoint and you guys don't really know, what was the decision-making process along the way, what is the significance of each result that we have, then it might not go so well. So I just wanted to make sure to keep you guys in the loop and make sure that you guys, know what's going on. All right. Well, I think that's it. Bye.